Okay, so one of our last sections is proof of concept for verifying QoS in a next generation network. So I figured first of all what I would do is we would talk about methods of actually implementing QoS, because it doesn't really matter if it's current generation or next generation networking, the actual method of implementation for QoS is the same. We're going to talk about things like legacy CLI, some modular QoS, auto QoS functions including VoIP and enterprise, and we're going to talk about some policy managers for QoS. One of the interesting things with our QoS policy manager is it allows you to across the board manage QoS. That's slightly different than the auto QoS because the auto QoS is more individual. So depending on the feature set that we're doing, remember that our goal is end-to-end quality of service. Features like our auto QoS for VoIP, it allows us to prioritize automatically our voice over IP traffic only. Because this is auto QoS and specifically designed for VoIP, what it does is it looks at the PDU, and the second it sees that the payload is VoIP, it auto prioritizes it. One of the problems with this though is it's only for VoIP. So there's another set of features called auto QoS for the enterprise or enterprise, which is used for network-based application recognition. Basically, just like VoIP, you predefine a specific application for it to recognize, and once the system recognizes that payload is from that application, it allows you to create a policy for that flow of traffic. Nice thing with this is because it's application-based, you can actually set different priority queues for different types of features. So that is kind of nice. Steps for implementing our QoS is first of all, it seems pretty straightforward, but this has always been an issue. Identify the type of traffic. Identify the priority. What traffic takes priority? And are you sure that your ranking is the appropriate one for your organization? This actually is set up for a QoS exam, and one of the biggest things is people do not do any form of business impact analysis or BIA type planning, and so even though they view specific applications as critical, that doesn't mean that management or, well, actually it's mainly management. I was going to say workers, but realistically it's management. They don't follow the same missions and goals that the overall organization is trying to promote. So our QoS policies have to be done only after a business impact analysis. That way we can have a critical rationale and justification for what prioritizing and what ranking our traffic actually is in. Once we've done that, again we divide it into classes. Highest priority, lowest priority. If it's mission critical, which has to be best effort versus least effort? What is okay to drop if best effort or least effort's not taken care of? What's super mission critical? What's highest priority? Right here, they say voice is always highest priority. I've been in organizations where voice was a secondary. It just kind of depends on, again, your organization. So once you actually divide it into our different classes, we have to define our policy. How much bandwidth or how much section of our bandwidth are we going to be sending to specific departments or applications or areas for our different defined classes. So what I mean by that is, let's say we do break this up into voice, mission critical, best effort, and then other applications that we can just put there if there's additional bandwidth. Well, how much are we giving to voice? How much, if we have, let's say, 100 megabit, are we dedicating half of it to voice? Are we dedicating 2/3 of it to voice? How much of the bandwidth are we actually going to carve out for voice? If we get two items, voice and mission critical, obviously they cannot equal 100% of the total bandwidth, so how much are we going to allow? What happens if there's major congestion? What order are we going to start dropping our packets? Those are all questions that we have to start thinking about when we start trying to find a QoS policy. Next is our precedence. So our standard for QoS is normally done by a layer 3 it's a layer 3 PDU, so that we can do our class of service. And how it really works is it's a flag or a switch inside our IP header that allows us to do our class, which that's our IP2OS. Again, it's 8 bits, so 1 byte, and within there you can prioritize it as anywhere between 0 and 7, thus allowing for us to rank them 0 to 7. So what is our classification? And that's a really big thing. So we organize them, we classify them. But what exactly does that mean? Our classification in terms of QoS specifically is the ability for a network device to identify different traffic types and divide them into different classes based on business requirements. Normally it is classified on the inbound or ingress interface. That way the router can prioritize it as it comes into it. That's just a small portion of our classification. Because that's the one portion of our classification, how does it actually process the egress? How does it handle all the ingress packets? If we have two things that are titled critical, what takes precedence? If we are doing a heavy load on our interfaces and we keep continuously receiving normal traffic and priority traffic, how much priority traffic flows before normal traffic? Is it a specific ratio? Like, do we do 2 packets of priority, 1 packet of regular? Or do we just allow priority first, and then only after that's done, then we do regular? It just kind of depends. Some of our classification tools, again, are our INBAR, which is our network-based application recognition. It could be policy-based, or even just done through an ACL. So, how do we do the marking? Because that's the big thing, is now that we have it, how do we mark it? And there's different methods of marking. QoS, which is a class of service, which we've already explained for our QoS. If we're doing frame relay, we have a BE bit. If we're doing MPLS, it's an X bit. If it's doing IP precedence, or it could also just be differential service code points. These are just different methods, and normally we only do a few of them. However, within larger enterprises, we have a much larger array of QoS classes that we can do. Normally, again, we just do 4 or 5, but in all reality, there are, it says 11 classes. I can remember 10 off the top of my head. I always forget 1 or 2 of them, but I want to say at least there are 10 heavily recognized class models for QoS. So let's talk about our first one, which is RCOS. So what it does is it allows for the IP header, which is defined by our 802.1p, which is a user priority field for our tagged 802.1q header. If you're using a Cisco proprietary ISL header, same thing, but it allows us to tag this user priority inside of our Ethernet frame layer 2. And again, normally we're allowed to use 0 through 7, but here 7 and 8 are reserved for typically and not use classified traffic. That's normal traffic. Normally for our QoS, 0 through 0 through 5, that's 6 additional addresses. And the higher the priority, the higher the number. So for our voice traffic, we want to assign it the highest usable. Again, 6 and 7 are special cases, because they're not normally used for classifying traffic. So 5 is our highest number for classifying traffic. Though there are some limitations for our QoS and our COS. So many dang acronyms. And that is if our packet is received on a non-trunking Ethernet port, and it may or may not actually process our frame header the correct way. Because what ends up happening is, the second they come in on a trunk port, they can strip away the priority markings, thus completely mitigating our class of service. So our marketing for our MQC, which is again is just marketing for our quality of service. It allows you to set an IP precedence, thus allowing you to set priority-based policy map of between 0 and 63, so 64 different variations. That way, you can classify and organize a little bit more fine-tuned. Because with our QoS, that's only 6 options. But what happens if you have a large enough organization where you need to be able to classify more? Also different locations being tied to a centralized or headquarter or data center type scenario. You have to be able to prioritize in a very specific way, but all of this is tied to your organization. If we're talking about our DHCP, again, that goes back to one of our previous, I think, Unit 2, which is our diff service field. Again, that is allowing us to do it per hop. And again, we can prioritize that between 0 and 63, thus allowing some form of heightened priority. Again, this is all for end-to-end communication. And this specifically, the DHCP, it's actually more located for forwarding. This is more specific for forwarding and queuing methods for per hop behavior. What I mean by that is, as it goes per device throughout a network, or even through an ISP's network, we can set per hop priority outside of our network. That doesn't mean that they actually have to adhere to them, but we can set it, or we can pay for that type of service so that they will accept it. If we're dealing with our per hop behavior, more specifically our frame relay, even though it goes to a frame relay switch, and how it functions within that frame relay we don't really work with. Same thing with our MPLS. We can set a specific value. Thus, we can guarantee at least a specific amount of bandwidth. Normally we do this for at least our voice because of the audio. The audio, again, having a real-time component to it. Assured forwarding, again, this is going to be for our high mission-critical traffic, and that just allows us to set priorities. Again, all of this is different variations of priority-based in next-generation and current-generation networks. Again, how are we going to flag these? Are we going to flag it highest? We're going to flag it medium. If we flag it AF2, for example, is that going to be equal priority for our AF3s? They're not. While it is medium priority, is it the low medium or is it the high medium priority? It's basically all about being able to classify our traffic to guarantee delivery and bandwidth. Here is another variation of our AF classes, our drop preferences, our binary DHCP. All of this again is how are we doing our flow. So what is this drop preference though? Our drop preference is a tiebreaker. So if we have two packets between of the same class during congestion, what method do we do to actually drop one packet versus sending it? And that's our drop behavior. Another important topic here is that you have to remember the higher class is always favored. Thus, the higher the class, the more priority it's going to be given. Class selector. Again, with the IP precedence device, it's going to use the first leftmost bits in the frame header. But again, it's all about being able to represent the ID 0 through 5 in binary. That's why it's using the first 3 bits. 0 will be all 3 zeros. If it was a precedence of 1, it should be 0, 0, 1, versus a precedence of 2, which should be 0, 1, 0, so forth. For our 7 bits, 7 bits should represent all 1s. 1, 1, 1, that should be a 1 in the 4, a 1 in the 2, and 1 in the 1 spot, thus equals 7. For our network-based application recognition, so this protocol discovery, again, it does a deep packet inspection to look at the payload. That way they could see what the application data really is. From that, they can determine its appropriate priority based off of the policy that is set. Again, it all is based off of an MBAR port map. It's not so much specific a port number, but it's based off of application. Though an interesting thing with port map, because I wanted to double check that and verify it. Port mapping for MBAR can also use default ports for a specific application if you're using a common application. So if you want to prioritize mail traffic, if we're using POP or SMTP, you could actually use their default ports, thus favoring those types of applications over others. And those, again, would you'd be using those common ports. Continue on with our MBAR. Our PDLMs does a packet description language module. It hopes in our MBAR discovery, and what that does is it looks at signatures, it looks at protocols, it looks at unique features of our individual packets to help prioritize traffic better. However, if we're doing any type of encapsulation, it doesn't work. So things like our ether channel, our tunneling, our crypto interfaces, nope. So how this works is IP MBAR, MPLM, and the file name. You could also do based off of protocols and ports, and all of that allows you to do priority based on either port or application. Again, this is Cisco predominant. I know this works within Cisco equipment. I'm not sure if it works with other equipment as well, but I know that this works in Cisco equipment. I tried doing this same type of setup with Juniper equipment, and I didn't have the same desired effect. So for after you run it, you can always verify that it's been correctly configured by doing a show IP MBAR protocol discovery or show IP MBAR port map. That way you could see if it's done. So how does that work if we're talking QoS within VPN tunnels? Because the tunnels are going to have encrypted payloads or encrypted headers or both. So how does it do QoS based off of encryption? So it ends up happening specifically with our Cisco iOS devices is it takes those 8 bits, or that 1 byte in the QoS, and it actually puts that inside our encrypted header. So an interesting thing here is, so when we do our VBN tunnels, if we encrypt the payload, the header is not encrypted, so we don't have to worry about the TOS byte. If we're doing header encryption, then we're going to have to worry about the TOS being also placed there. And with most things, you can test it using a show interface, the type of interface, and seeing the QoS preclassification on the queuing strategy line. That's going to be really important. When you look at a show interface and then you go specifically to that interface, you're looking at a huge line of text, so you want to make sure you're looking at the queuing strategy line. One of the nice things is with mbar is it works with most things. However, it does not work for low-end Cisco switches, and ACLs are the only supported method. So with Catalyst switches specifically, I know this is true for the Catalyst 3500 series and below. It doesn't work. However, I have noticed that you can get it to work with a Catalyst 6500 series switch, but those are core level switches and those are fairly more expensive, so that's slightly different. Also with the core level switches, you'll probably be doing a different type of QoS because those are more for MPLS anyway, but I wanted to put that out there just so that you know. And for a Cisco Catalyst switch, would be doing a MAC access list extended. It has to be a extended ACL, and then you can do a deny action or ignore any ACLs that are used for the classification. For MLS QoS Trust, it's all right there. The MLS QoS Trust DHCP, it is just the trust for the specific DHCP number. So what we have to end up doing is on our MLS QoS COS value is we have to start prioritizing. We have to give them a number. So after that, we can start talking about congestion management. Because one of the issues with QoS is, so it will actually queue the messages to be sent out, but what happens when the device is overloaded? And that becomes an issue because that's where our congestion comes in. So we have multiple queuing methods. We have priority queuing, we have custom queuing, which both of those are obsolete. We have weighted fair queuing, which that's a more common one. We also have a class-based weighted fair queuing. That's our C, B, W, F, Q. Have to love the acronyms. But what that does is it allows you to do weighted fair queuing off of classes. That's why prioritizing is so important, because most of the time our mechanisms are going to use that class base to do other features. And then we also have a low latency queuing so that we can have lower latency for the specific requirements. For our weighted fair queuing, normally does not require any configuration. It's just first come, first serve. If there is prioritizing, it prioritizes the higher priority first. Priority is given to low bandwidth traffic. It also allocates additional bandwidth to higher preceding flows. So if they start seeing that there are higher flows for a specific task or a specific stream, it actually starts dedicating additional bandwidth. The issue with this though is it's not ideal for real-time traffic, for example, voice. So how does it work? It dynamically creates queues for each flow. A flow is determined based on a specific type of matching, normally source and destination addressing. It could also be based off of TOS values. And essentially what ends up happening is they start seeing patterns, and they can start doing flows based on those patterns. Part of that can also deal with our hold queues and our congestion discard threshold. Essentially what ends up happening is how many packets can it hold in the queue, per interface. At what point do we start discarding packets? If our device is overloaded, how long do we have to wait till we start just throwing away the items that we've deemed not overly important? Interesting feature for our class-based is it's good for pretty much everything but voice and video. Because again, it guarantees chunks of bandwidth per class. And it's not always supported on sub-interfaces, so VLANing is going to be an issue. But the fact that it's not good for video and voice is not going to be one of our go-to types of QoS. However, the nice feature with all of this is you can use multiple QoS ways per device, per network. You're not limited to just one type of QoS. Bandwidth is also bandwidth percentage. Could also be dealing with throughput. I mean, we can classify these several different ways. Our low latency queuing, though, is perfect for our voice. It uses priority queuing. This is going to be the best one for our voice since it's low latency queuing. It will allow you to do priority queuing before all other devices or all other packets. So what ends up happening is if multiple packets are coming in, this is processing priority queues first. Even if there is a lot of priority queues first, it's going to process all priority queues before anything else. For all other traffic, first in, first out, FIFO. When there is not a priority queue there. Though you can set it up in such a way so that your priority queue is going to be 50% of the bandwidth, everything else will be your FIFO. And then if the priority queue is less than your 50% of your bandwidth, then it starts auto-scaling so the FIFO uses more. You can set it so that priority queuing can be burstable, so that it may have dedicated 20%, then if there's a lot more traffic than normal, it can burst up to 50%. It just kind of depends on the policy that you set. One of the big issues here is, what does it mean by policed? So you can set priority so that it will not consume more bandwidth, and then if it tries to consume more bandwidth, they just start dropping. One of the nice things here is that allows you to hard code policy for preventing starvation of other classes. That's a really big thing here, because if you set your priority queuing too high, it actually starts starving or taking bandwidth from all other classes. That may or may not be okay, just kind of depends on, again, your environment. On Cisco switches, normally you can set up 4 types of queuing, and the main thing that you're configuring is our drop threshold. And kind of the big thing here is you set it so that it will drop standard queues and it doesn't drop priority queues. However, that's not always the case, so sometimes you're going to have to be able to set drop priority queues. It's just you have to be able to configure it in such a way so that it drops priority queues last. So let's look at a few different types of switches. On a Cisco Catalyst 2950/2960, you can actually set strict priorities. That way you help kind of shorten delay within voice and video. You can set priority for mission critical traffic as well, but that way you can guarantee X amount of bandwidth available for the lower latency items that are dependent. What all that really means is things that are lower latency, things that have a real-time component, they're going to need lower latency, thus they need to be able to be queued higher. That way they can be sent out quicker. So let's talk about weighted round robin. So round robin is, it just kind of goes, if you have 5 queues, it goes through first queue, second, third, fourth, fifth, then restarts. That way everyone gets equal chance to send. But the problem with equal round robin is, what happens if your first queue is voice you might need additional space for that. So we can do a weighted round robin, so that certain queues get a higher priority or a higher weight. And so it could go 1, 1, 2, 3, 4, 5, 1, 1, 2, 3, 4, 5. Or you can queue it however specific way that your network is requiring it. The question then becomes, is weighted round robin good for voice? Voice is still degraded using round robin or weighted round robin, though if you set a weighted round robin with a strict priority queue, it can help alleviate some of this. It's still not the best. There can still be some degrade, but it's not as bad. Okay, so now let's get back into some of our next generation topics, and that's going to be our policing and our shaping. So how do they differ? Policing drops, or it can do remarks on excessive traffic. So if it sees, like YouTube for example, there's a lot of excessive traffic from or for YouTube or from a specific computer, you can start throttling it back. Shaping will delay it. So instead of dropping it completely, it can delay it. That way, again, if you have one computer that is just excessive, you can control if it will be dropped or delayed. However, all of this is configurable, because obviously a server, for example, is probably going to have excessive traffic. You don't want the traffic from that server dropped. You may not want it delayed. So it gives you the option of doing one or the other, or doing nothing to it and just allowing that traffic a higher priority. Though you could say that certain applications on that server or specific ports coming from that server are shaped so that it will allow resources from other areas to be sent. For example, if it's a mail server and a file server, you can set it so that the shaping will shape the traffic for mail. That way it's allowing more bandwidth for the file sharing. That's just an example. I mean, you can kind of organize it however you would like, but again, it's really dependent on your organization, policies, procedures, management, their needs. There's just a lot going there. Okay, so for policing, so you can set applications and bandwidth restrictions for specific types of priority. For example, if it's going to be a peer-to-peer type file sharing application, this says LimeWire, but I don't think LimeWire has been used very much lately. But you could be looking at torrent traffic, for example. You can now limit that. Or if you have a system event manager, you can just completely drop that, if that's the policy. Or you could have a policy that states, excessive traffic when the network is congested, automatically start dropping peer-to-peer or torrent traffic. That way, that will alleviate some of the congestion. So how does policing and our shaping really take effect? And it's actually based off of a token and token bucket. What ends up happening is it allows you to start placing packets or a portion of a packet as a token into a bucket. And what happens is once the bucket is full, that queue is then sent. You can prioritize it so that the priority packets come in, they put their token in a much smaller bucket, and that bucket is sent to the queue once it's filled. But again, you can kind of vary the size of the individual buckets. That way you could have priority traffic queued first or queued faster. This kind of depends on, again, your organization. So let's say, for example, we have two types of traffic for our network. We have voice and data, and our data is not overly important, so we're going to say every 10 packets of data, then we'll queue it, versus every 5 packets of voice, then we'll queue it. So it ends up happening as it comes in the interface, the device will, for each packet, put a token in the bucket, and once the bucket is filled for again, our voice, so once 5 packets are received, it auto queues it out. That way, depending on how many packets it's getting, it will start organizing or classifying its queues based off of those packets. And every 10 packets of data, then it will send it. That way, it should be sending 2 packets or 2 queues for our voice for every 1 packet for our data, assuming that all of it's coming equally. If one's coming faster than the other, then again, it's all going to look at how many tokens are coming really in. So if we have 100 packets coming in, we're assuming that half will be data, half will be voice, and that explains that example. But what happens when it's 60-40? Again, for every 5 tokens for voice, it will send it. So if it's 60 data, 40 voice, for the queuing of all of that, we're looking at least 6 data packets to be sent to the queue versus our 8 voice. Because again, our voice in our example, for every 5 packets of voice, it sends it to the queue. So that's 1 big packet sent out. The next 5 gets sent out. So again, it just kind of depends on your infrastructure, your network, your design, what method. But what happens when there's not enough tokens? What ends up happening is, if you have just the base token process installed, once it stops receiving packets for a specific type of application or packet or appropriate PDU for voice or data traffic or whatever, it starts delaying or dropping those packets. So let's say we have to have 5 tokens to send a voice packet, but it was such a small call, we only got 4. Well, the bucket won't send until it gets 5, and after X amount of time, it just drops all 4 tokens because they never received the 5th token for it to be able to send. So that's an issue with a single bucket system. So an interesting note here for our policing is our metering. And that's what service providers do to limit customers' upload and download speed. So what ends up happening is you pay for a specific bandwidth, upload and download speed for internet. And what ends up happening is they apply some type of policy so that you can get your specific speed. And that's going to be your committed access rate. It can go higher, but you're always going to be guaranteed at least a specific type of speed. Normally these are implemented at the access or distribution layers, never at the core. And again, this is going to be shaping, not policing, because it's not going to drop your packets once you get to your threshold of your limit. It will just start slowing it down. So let's look at another example for our traffic shaping. So in the example that I've been trying to go with has been a company headquarters. It has a 1 gigabit fiber link over a WAN, and there is a branch office. And the branch office is connecting via a 64K via serial link. The data being sent from HQ would obviously way overwhelm our branch, but we can actually do shaping so that when it knows it's going to be connecting to our branch office, it kind of shapes it so that it only sends in our appropriate speed so that the branch office doesn't get overwhelmed. What it does, it will help limit it to the 64 kbps. That way it's only getting what the branch office can take. That's the nice thing with our shaping. That way the router or the device will just queue it, and it will just wait, and it will send eventually. It's just because of the limited bandwidth going to the branch office, it just kind of waits its turn to be sent. What happens to the excess bandwidth? The excess bandwidth, assuming that split horizon is there, the rest of the bandwidth will allow the company to do just normal connections to other locations or to the internet or elsewhere. Our shaping is applied typically to the exit or outbound or egress interface, and it will not allow you to do it based on an ingress, because our traffic shaping, it's not so much coming in, it's how we're doing the shaping going out. And we can do our shaping by average, or by peak, or by percentage. Again, it's all about variation. We can do class-based traffic shaping, because again, if we classify it, we categorize it, we can prioritize it. If we prioritize it, we can shape it based off of the criteria. That way, things like our frame relay or our MPLS, we can make sure that we are shaping it to the specific needs or speeds of our connections. Because again, if we're at a higher bandwidth location, if we're going to be sending data to a lower bandwidth location, we can't overwhelm them. We have to send at a speed where they can receive and still function without them getting overwhelmed. So how can we mitigate some of that? So we can mitigate some of that by our link efficiency, and a big part of that is our payload. That's the actual portion of our packet that is going to be data, and are we going to be able to compress it? And we can compress it using predictors, stackers, or other forms of compression. We can do this with hardware, we can do this with software, we can do this on the header compression. Again, our goal here is to reduce our headers so that we can save bandwidth. One of the problems that I keep seeing is as we get faster and faster connection speeds, our QoS is slowly going away. Just so that you guys know, this is the PowerPoint that I was able to use for a QoS course. So this goes into QoS, like the nitty gritty. Not that many people have to go into QoS, because again, our link speeds are getting faster. So we're not having to deal with a 60K or 64K connection. Even our slow connections are still megabits, not in the Ks anymore. And even then, our bandwidth pricing for businesses and homes, they've been drastically reduced so that we can get faster connections. The other day, we actually just installed a dual 10 gig connection for their internet, and that was synchronous. So 10 gigs down, 10 gigs up, and we installed dual. So one was a primary, one was a backup, and that way they could send to the internet at 10 gigs. And we were actually able to do that at 4 locations. The 5th location can only do a gigabit fiber, and that was actually cheaper than our like 100 megabit connection that was out there. So our bandwidth is no longer as big of an issue. This was really true 5-6 years ago, but in our current generation and our next generation networking, because of the increase in our bandwidth, it really is going away. Bandwidth is not so much always the connection that we have, it's also sometimes the connection that the equipment that we have can send and receive. So that's actually been a huge issue at our ISP level, because for the longest time they could not have devices that could switch so quickly or could route so quickly. As we've seen in previous material, we have our CSR type routers that are made to switch and made to route terabits of data a second. So again, our bandwidth is finally getting to the point where we can send and receive mass amounts of data. One thing that I thought was really important, since we do talk a lot about voice, was doing our calculation bandwidth for our voice. And so what we end up having to do is we convert our bytes to bits. So if we are dealing with 200 bytes, there are 8 bits per byte, so we're looking at 1600 bits. So now let's look at voice specifically. we want our voice to sample ranges from 20 to 30 milliseconds of audio. That means there's going to be 50 packets per second for between 20, and if we're doing a 30, we need at least 33 packets per second. So let's assume that we're just doing our 20 milliseconds. So if we have 1600 bits, we have 1500 packets per second, that's 80,000 bits per second. So that means for one voice phone call sampling 20 milliseconds, we're going to have at least a dedicated link or a dedicated pathway for our 80 kilobits per second connection. And that's also assuming that we're using a specific codecs. The G711 requires our 80 kilobits. If we're using a newer codecs, 729, it's 24 kilobits per second. And that's per call. So that's something you need to think about. Okay, now that we are done, we covered things like our QoS procedures. But how do we know if it works or not? That's always been a big one, is how do we know if our QoS fully functioned or not? One of the biggest ways that I found to do this is actually testing with and without QoS. So we do a straight baseline test without QoS, and then we see traffic flow. Once we have that data, we do it again, and we do the same thing with QoS. And again, we look at our traffic flow. Then we compare our baseline, non-QoS, with our QoS. That way we can see the overall efficiency. Because sometimes QoS is not always worth it. Most of the time it is, but again, it really just kind of depends on your environment. Okay, so that's all for the material that I had for this week. One of the big things that I did want to talk about was our IPs, our individual assignments. Make sure that we're meeting our page requirements, that we're meeting our APA guidelines for our formatting. If you're not sure how to format an APA, let me know. We have a great library service, we have great tutorial services, we have a great writing service. We also have a really good training link for our APA. You are not going to get away from APA with higher level writing. It's no longer the case. If you search APA formatting, you should be able to find numerous resources online. If nothing else, currently there's an APA 6 manual that gives you all the nitty-gritty on APA. And people keep asking me, well, why is APA that big of an issue? Well, the problem with APA is that's our guidelines for higher level academic writing. And so we have to make sure that we're adhering to them. That way, if anyone within a scholarly level is looking at your paper, it's formatted a very specific way. And again, that's all APA format and guidelines. Our references, we need to be building off of existing work. Remember, if nothing else, we are building from the existing body of knowledge. You provide the sources, you provide your citations for you getting your sources, but that way, when you say something, you can get from them support. For example, if I say the sky is blue, you can take my word for it, or I can provide you scientific data, or I can provide you a citation to some form of scholarly article that says that it's blue, and then I'm just restating it, but I'm providing where I got my information. Thus, you're not just taking my word, you're taking my reference word as well. Because remember, when we do writing, it's about credibility, reliability. Are we getting information that is credible and reliable? And that's a really big thing here. For our discussion posting, remember, 3 times at least, make sure to be responding with citations in almost every one of your posts. We're never getting away from citations. They are that important. Again, they have to be in APA. I cannot drill the APA portion enough. Well, I hope you guys have a great afternoon, and I'll see you next time. Bye.